Hello there, and welcome to the Drowsy Inquirer. I'm so glad you found your way here tonight, wherever you may be in this vast and spinning world. Perhaps you're lying in bed, the day finally behind you. Perhaps the house has grown quiet, and the only sound is your own steady breathing. Or maybe you're somewhere else entirely, seeking a moment of stillness in a world that so rarely offers one. Tonight, we're going to drift through something you've known your entire life, something so familiar that you may have stopped noticing its wonder. We're going to explore water, not just the water you drink or the rain that taps against your window, but the molecule itself, the ancient traveler, the quiet architect of everything alive. Water is strange, wonderfully, impossibly strange. It breaks the rules that other molecules follow. It flows uphill through the tallest trees. It expands when it freezes, which almost nothing else does. It has cradled every living thing that has ever existed on this planet, and it may be doing the same on moons and planets we have yet to visit. From the darkest trenches of the ocean to the icy geysers erupting on distant moons, from the single tear rolling down a cheek to the vast clouds swirling above hurricanes, water is everywhere, and yet most of us have never truly stopped to wonder at it. Tonight that changes. We'll wander through the hidden architecture of the water molecule, drift into the deepest places of the ocean, float through clouds, freeze into ancient glaciers, and travel to the edges of our solar system where water hides in unexpected places. If this kind of quiet curiosity brings you peace or helps you drift toward sleep, consider leaving a like or subscribing. It helps other restless minds find their way here too, one sleepy soul at a time. But for now, let yourself settle. Take a breath. Let your thoughts soften at the edges. And let's begin this slow and gentle journey through the molecule that made everything possible. Let's start with water itself, the molecule, and the beautiful strangeness hidden within its simplicity. A water molecule is made of just three atoms, two hydrogen atoms and one oxygen atom, bonded together in a shape that looks almost like a tiny boomerang. If you could see it, you would notice that it isn't straight. The two hydrogen atoms don't sit opposite each other. Instead, they're bent at an angle of about 104.5 degrees. This small bend might seem like a minor detail, but it changes everything. Because of this angle, one side of the water molecule carries a slight positive charge, and the other side carries a slight negative charge. The molecule becomes polar, like a tiny magnet with two ends. And this polarity is the source of almost every miraculous thing water does. It's what allows water to dissolve so many substances. It's what gives water its surface tension, letting insects walk on ponds without sinking. It's what makes ice float, protecting the creatures beneath frozen lakes. All of this from a simple bend in a molecule smaller than anything you could ever see. There's something quietly profound in this. The shape of something so small, so invisible, it determines the fate of oceans, the rhythm of weather, the very possibility of life. The angle of a molecule, decided billions of years ago in the hearts of dying stars, still echoes through every raindrop, every river, every cell in your body tonight. Water molecules don't exist in isolation. They reach out to each other constantly, forming connections called hydrogen bonds. These bonds are not permanent. They form and break with astonishing speed, lasting only a trillionth of a second before dissolving and reforming with a different neighbor. In a single glass of water sitting on your nightstand, trillions upon trillions of these bonds are forming and breaking right now, in this very moment, faster than anything you could ever perceive. The water looks still, it looks calm. But at the molecular level, it is a blur of constant motion, a dance that never stops. This dance is what gives water its fluidity. It's what allows water to flow around obstacles, to seep into the smallest cracks, to find its way through soil and stone and the winding vessels of your circulatory system. The hydrogen bonds are strong enough to give water structure, but weak enough to let it move. Imagine a crowded room where everyone is holding hands, but the handshakes last only a fraction of a second before everyone switches partners. The room stays full, the connections remain, but the flow never stops. That is water. That is the invisible choreography happening in every drop. Most substances become denser as they cool. Their molecules slow down, pack together more tightly, and the substance contracts. This is true for almost everything in the universe. But water, once again, refuses to follow the rules. As water cools toward freezing, it does become denser, but only until it reaches about 4 degrees Celsius. Below that temperature, something strange happens. The water molecules begin to arrange themselves into a crystalline structure, and this structure takes up more space than the liquid form. Ice becomes less dense than water, and so ice floats. This might seem like a small curiosity, but it is one of the most important accidents in the history of life. When a lake freezes in winter, the ice forms on the surface first. It creates a floating blanket that insulates the water below, keeping it liquid, keeping it warm enough for fish and frogs and countless other creatures to survive until spring. If ice sank, lakes would freeze from the bottom up. Life in fresh water would be nearly impossible, when the entire rhythm of aquatic ecosystems would collapse. But because of that strange molecular arrangement, because water breaks the rules, life persists beneath the frozen surface, quiet and patient, waiting for the thaw. Have you ever watched a drop of water beat up on a leaf, forming an almost perfect sphere before rolling off the edge? Or noticed how some insects can walk across the surface of a pond without breaking through, as if the water were covered by an invisible skin? This is surface tension, and it exists because of those hydrogen bonds we spoke about. At the surface of any body of water, the molecules have no neighbors above them. They can only bond with the molecules beside them and below them. This creates a kind of net, a molecular film stretched across the surface, strong enough to support small weights. Water striders, those delicate insects with their long, thin legs, have evolved to take advantage of this invisible membrane. Their legs are coated with tiny hairs that trap air, spreading their weight across the surface without breaking through. They skate across ponds as if gliding on glass. Surface tension also shapes raindrops. As a drop falls, it isn't teardrop-shaped, as artists often draw it. It's more like a tiny hamburger bun, slightly flattened on the bottom by air resistance, held together by the cohesive pull of its own molecules. Every drop is a small act of molecular architecture, a fleeting sculpture formed in the sky. Water is often called the Universal Solvent, and while that name is a slight exaggeration, it contains a deep truth. Water can dissolve more substances than any other common liquid. Salt, sugar, gases, minerals, proteins, acids, the molecular building blocks of life itself, all of them can be pulled apart and carried within water's embrace. This dissolving power comes from water's polarity. When a crystal of salt is dropped into water, the water molecules surround each sodium and chloride ion, pulling them away from the crystal and into solution. The positive ends of the water molecules attract the negative chloride ions. The negative ends attract the positive sodium ions. Piece by piece, the crystal disappears. This is why the ocean is salty. Rivers carry dissolved minerals from the land and deposit them into the sea. The water evaporates, rises, falls as rain, and the cycle continues. But the salt stays behind, accumulating over billions of years. The ocean is a record of all the rocks that have ever been washed by rain and carried to the sea. And within your own body, water is doing the same work right now. It carries nutrients to your cells, dissolves waste products, transports hormones and signals. Every chemical reaction in your biology happens in water, surrounded by water, made possible by water. You are, in a very real sense, a walking solution. Water has an extraordinary ability to absorb and hold heat. This property, called high specific heat capacity, means that water can soak up a great deal of thermal energy without its temperature rising very quickly. It also means that water releases heat slowly when it cools. This is why coastal cities have milder climates than inland ones. The ocean absorbs heat during the summer, moderating the warmth. In winter, it releases that stored heat, keeping the air from becoming too cold. Cities like San Francisco and London owe their temperate weather to the vast body of water nearby, acting as a thermal buffer. On a larger scale, the oceans regulate the entire planet's climate. They absorb heat from the sun, distribute it through currents, and release it gradually into the atmosphere. Without this thermal stability, the Earth would swing between deadly extremes, scorching during the day and freezing at night, like the barren surface of the moon. Even inside your own body, water serves this function. It helps maintain your core temperature, absorbing the heat generated by your muscles and organs, distributing it evenly, releasing it through sweat and breath. You are, in a very literal sense, a water-cooled system. Imagine a tree, one of the tall ones, a redwood perhaps, stretching over 100 meters into the sky. Now imagine the water inside that tree, traveling from the roots buried in the soil all the way to the leaves at the very top. How does water climb that high, against the pull of gravity, without any pump? The answer lies in two forces working together: cohesion and adhesion. Cohesion is the attraction between water molecules themselves, those hydrogen bonds that hold them together. Adhesion is the attraction between water molecules and other surfaces, like the walls of the tiny tubes inside a tree. When water evaporates from the leaves at the top of the tree, it creates a slight vacuum, a negative pressure that pulls on the column of water below. Because water molecules are so strongly bonded to each other, they don't break apart under this tension. If they hold together like links in a chain, pulling the water upward, molecule by molecule. This process is called transpiration, and it moves millions of liters of water through forests every day, silently, invisibly, without any energy expended by the tree itself. The water rises on the strength of its own molecular bonds, lifted by the sun's heat and the thirst of distant leaves. When water evaporates from your skin, you feel cooler. This is not just a sensation, it's physics. Evaporation requires energy, and that energy is drawn from whatever surface the water is leaving. When sweat evaporates from your forehead, it carries heat away with it, lowering the temperature of your skin. This evaporative cooling is one of the most efficient temperature regulation systems in nature. Humans are exceptionally good at it. We can sweat more than any other animal, which is part of why our ancestors could hunt in the midday heat of the African savanna while other predators rested in the shade. But it's not just bodies that use this trick. The Earth itself cools through evaporation. Water rising from oceans, lakes, and forests carries heat into the atmosphere, where it's eventually radiated into space. The entire planet breathes in a sense, exhaling water vapor and shedding warmth. Even something as simple as a wet towel draped over your forehead on a hot night is harnessing the same principle. The water draws heat from your skin as it transforms into vapor. It's a quiet exchange, a small transaction between liquid and air, but it has been keeping living things cool for billions of years. Water is the only common substance that exists in all three states of matter within the normal temperature range of Earth's surface. Solid ice floats on liquid water. Water vapor drifts invisibly through the air, and all three forms are present on this planet at this very moment, cycling endlessly from one state to another. This is rare in the universe. Most planets are either too hot or too cold to allow such variety. On Venus, any water would instantly boil away. On Mars, it sublimates directly from ice to vapor without passing through the liquid phase. But Earth sits in a narrow band of temperature and pressure where water can exist as a solid, a liquid, and a gas, sometimes all at once. This is what makes our planet alive. The water cycle, that endless movement of water through evaporation, condensation, and precipitation, it is powered by this triple existence. Without it, there would be no rain, no rivers, no replenishment. The continents would be barren rock, and the oceans would slowly evaporate into space. Tonight, as you rest, water is moving through all three states somewhere on Earth. Snow is falling in the mountains. Rivers are flowing toward the sea. Clouds are forming over warm oceans. The cycle never pauses. It has been spinning since the planet was young, and it will continue long after we are gone. There is another form of water, one that looks identical to ordinary water, but carries a subtle difference. It's called heavy water, or deuterium oxide. In heavy water, the hydrogen atoms are replaced by deuterium, a heavier isotope of hydrogen that contains a neutron in addition to the usual proton. Heavy water is rare, making up only about 1 part in 6,000 of all the water on Earth. But it exists everywhere, mixed in with the ordinary water you drink, the rain that falls, the oceans that cover the planet. You have swallowed heavy water without ever knowing it. The differences are small but measurable. Heavy water freezes at a slightly higher temperature and boils at a slightly higher point. It feels almost identical, looks identical, but its molecules are just a little heavier, a little slower to move. In laboratories, heavy water is used in nuclear reactors and scientific experiments. But in nature, it simply exists, a quiet variation on the theme, a reminder that even something as familiar as water contains hidden complexity. The universe, it seems, likes to offer options, even at the molecular level. If you cool water very carefully, and without any disturbance, without any impurities to trigger crystallization, something remarkable can happen. The water can remain liquid far below its normal freezing point. This is called supercooled water, and it exists in a fragile temporary state, balanced on the edge of transformation. Supercooled water is common in clouds. High in the atmosphere, tiny droplets of water can remain liquid at temperatures as low as -40 degrees Celsius, waiting for a speck of dust or a crystal of ice to trigger their transformation. When that trigger comes, the freezing happens almost instantly, spreading through the droplet in a flash. You can demonstrate this at home with care. A bottle of very pure water, cooled slowly in a freezer, can remain liquid even when far below zero. But tap the bottle sharply or drop in a small piece of ice, and the entire contents will freeze before your eyes, solidifying in a wave from the point of disturbance. There's something almost magical about it. Water holding its breath, waiting for permission to become ice. It's a reminder that the world is not always what it seems, that matter can exist in between states in quiet suspension until the right moment arrives. Now let us leave the molecule itself and travel outward, into the vastness where water truly shows its power. Let us sink beneath the waves and drift into the ocean. The ocean covers 71% of Earth's surface. It is not a single body of water, but a connected system, one continuous mass that wraps around the continents, deeper in some places than any mountain is tall. If you could remove all the water from the ocean and stand on the exposed seabed, you would find landscapes more dramatic than anything on land, canyons and ridges and plains stretching beyond sight. Most of us will never see the true ocean. We see only its surface, its edges, its beaches and harbors. But beneath that glittering surface lies a world of darkness and pressure, of strange creatures and ancient currents, of silence so complete that it would unsettle you. Tonight, imagine yourself sinking slowly through that water, passing through layers of blue that deepen into black. The sunlight fades, the temperature drops, the pressure builds, and yet life persists, even in the darkest places, even where no light has reached for a billion years. The ocean is not still. It moves constantly, driven by wind, by temperature, by the rotation of the Earth, by the pull of the moon. And beneath the surface currents that sailors have known for centuries, there are deeper, slower rivers of water that circle the entire planet. This is the thermohaline circulation, a global conveyor belt driven by differences in temperature and salinity. In the North Atlantic, cold, salty water sinks toward the ocean floor because it is denser than the warmer water around it. This sinking water flows southward along the bottom of the ocean, eventually reaching the Southern Ocean, where it rises again and begins its long journey back. A single molecule of water caught in this circulation might take 1,000 years to complete the loop. It would sink in the frigid waters near Greenland, drift along the dark sea floor for centuries, rise in the Pacific or Indian Ocean, and eventually find its way back to where it started. A millennium-long journey, repeated endlessly. This circulation carries heat from the tropics toward the poles. It regulates climate. It distributes nutrients. It connects every ocean on Earth into a single, slow-breathing system. And it happens in silence, beneath the waves, invisible to everyone on the surface. In the Western Pacific Ocean, there is a place where the seafloor drops away into unimaginable darkness. This is the Mariana Trench, the deepest place on Earth, a crescent-shaped scar in the ocean floor that reaches down nearly 11 kilometers below the surface. At the bottom of the Mariana Trench, the pressure is over 1,000 times greater than at sea level. If you could somehow descend to that depth without protection, the water would crush you instantly, compressing your body into something unrecognizable. Light does not reach here. The temperature hovers just above freezing. It is one of the most hostile environments on the planet, and yet life exists even here. Small crustaceans, translucent shrimp, strange fish with bioluminescent lures, all have adapted to this world of eternal darkness and crushing weight. They feed on the slow rain of organic matter drifting down from the sunlit waters far above, a faint connection to a world they will never see. When explorers first reached the bottom of the trench, they found something unexpected: a plastic bag. Even in the deepest place on Earth, the marks of humanity had already arrived. The ocean connects everything, carries everything, forgets nothing. The ocean is not a uniform body of water. It is layered, stratified by temperature and light into distinct zones, each with its own character, its own inhabitants. Near the surface lies the sunlight zone, the epipelagic, where light penetrates and photosynthesis is possible. This is where most ocean life exists, where plankton bloom and fish school and whales rise to breathe. Below that is the twilight zone, the mesopelagic, where light fades to a faint blue glow, where creatures have enormous eyes to capture every last photon. Deeper still is the midnight zone, the bathypelagic, where no sunlight reaches, where the only light comes from the creatures themselves, glowing with bioluminescence. And below that lies the abyssal zone, a realm of near-freezing water and crushing pressure, where the seafloor stretches in endless plains of sediment. At the very bottom are the trenches, the Hadal zone, named after Hades, the Greek god of the underworld. Each layer is colder, darker, more pressurized than the one above, and yet each layer contains life, adapted to its specific conditions, thriving in ways we are only beginning to understand. The oceans are salty, but lakes and rivers are not. This difference seems obvious once you notice it, but the reason behind it reveals something beautiful about the water cycle. Rain falls on the land, and as it flows across rocks and soil, it dissolves tiny amounts of minerals, including sodium and chloride, the components of salt. Rivers carry these dissolved minerals to the sea, where they accumulate. When the water evaporates from the ocean surface, it leaves the salt behind. Over billions of years, this process has made the ocean saltier and saltier. Lakes and rivers, by contrast, are constantly refreshed. Rain falls, flows through, and carries minerals onward to the sea. The water doesn't stay long enough to become salty. It's a matter of residence time, how long the water remains in one place before moving on. The ocean is old. Some of its water has been there for millions of years, cycling between surface and depth, accumulating the minerals of countless rivers. It is, in a sense, the final destination of every drop that falls on land. Everything washes to the sea eventually. In the darkest parts of the ocean, where no sunlight reaches, something extraordinary happens. Creatures make their own light. This is bioluminescence, the production of light through chemical reactions within living cells. Imagine drifting through the midnight zone and seeing flashes of blue and green in the distance, lights that pulse and shimmer like underwater stars. Some creatures use this light to attract prey, dangling glowing lures in front of their mouths. Others use it to communicate, sending signals to potential mates. Some flash brightly when attacked, hoping to startle predators or attract larger predators to attack their attackers. Bioluminescence has evolved independently more than 50 times in the ocean. It is one of the most common adaptations in the deep sea. More common than eyes, more common than fins. In a world without sunlight, life has learned to carry its own. And if you ever find yourself on a dark beach at night, watching waves crash with an eerie blue glow, you are witnessing the same phenomenon. Tiny dinoflagellates, disturbed by the motion of the water, are releasing their light. The ocean, even at its edges, remembers how to shine. Sound travels differently in water than in air. It moves faster, nearly 5 times faster, and it can travel much farther, carrying across entire ocean basins without fading. Whales have known this for millions of years. Their songs, low and haunting, can cross thousands of kilometers, reaching other whales on the far side of an ocean. In the days before motorized ships filled the seas with noise, whales could communicate across distances we can barely comprehend. There is a layer in the ocean called the SOFAR channel, a depth where sound waves become trapped and travel with minimal loss. Sounds entering this channel can propagate for enormous distances, bouncing between the layers above and below, never quite escaping. Whales seem to know about this channel instinctively, singing at just the right depth to maximize their reach. And today the ocean is much noisier. The hum of ships, the ping of sonar, the rumble of underwater construction, all of these sounds interfere with the ancient conversations of marine life. The whales still sing, but the ocean that once carried their voices has become crowded with other sounds. Coral reefs are sometimes called the rainforests of the sea, and the comparison is apt. Though they cover less than 1% of the ocean floor, they support nearly a quarter of all marine species. They are explosions of color and life in waters that would otherwise be relatively barren. Corals themselves are animals, tiny polyps related to jellyfish, but they live in partnership with photosynthetic algae called zooxanthellae. The algae live inside the coral's tissues, producing sugars through photosynthesis, feeding their hosts. In return, the coral provides shelter and access to sunlight. It is a relationship that has existed for millions of years. When the water grows too warm, this partnership breaks down. The algae are expelled, and the coral loses its color, turning ghostly white. This is coral bleaching, and it can kill entire reefs if the stress continues. The corals can survive for a time without their partners, but they are weakened, vulnerable, unable to grow. Reefs around the world are bleaching more frequently now, stressed by warming oceans. But they are also resilient, capable of recovery if given time and cooler conditions. The partnership between coral and algae is ancient and adaptive. It has survived ice ages and mass extinctions. Whether it can survive the current changes remains an open question. And now let us rise from the depths of the ocean and travel upward into the sky, where water takes another form. Every drop of rain that falls, every snowflake that drifts to the ground, every cloud that passes overhead is part of a cycle that has been spinning since the earth was young. Water evaporates from the surface of oceans, lakes, and rivers. It rises into the atmosphere, cools, condenses into clouds, and falls again as precipitation. Then it flows back to the sea, and the cycle begins anew. This is the water cycle, and it is the engine of all weather, all climate, all fresh water on Earth. Without it, the continents would be deserts, and the oceans would slowly evaporate into space. The cycle is powered by the sun. Solar energy heats the surface of the water, giving molecules enough energy to escape into the air as vapor. And the vapor rises, carried by convection and wind, until it reaches altitudes where the air is cool enough to condense it back into liquid droplets. These droplets gather into clouds, and when they grow heavy enough, they fall. It sounds simple, but the details are endlessly complex. The cycle moves an almost incomprehensible amount of water, over 500,000 cubic kilometers every year, enough to cover the entire Earth in a layer a meter deep. And it has been doing this for billions of years. The same water, cycling endlessly, never lost, never created, only transformed. Clouds seem solid from a distance, like cotton mountains floating in the sky. But if you could rise up into one, you would find yourself surrounded by nothing more than a fine mist, billions of tiny water droplets suspended in air, each one so small that it floats on the slightest breeze. A cloud begins with evaporation. Water molecules escape from oceans, lakes, puddles, leaves, and skin, rising invisibly into the atmosphere. As they rise, the air grows cooler, and eventually the vapor reaches a temperature where it can no longer remain a gas. It condenses, but not onto nothing. Each droplet needs a tiny particle to form around, a speck of dust, a grain of pollen, a fragment of sea salt carried aloft by the wind. These particles are called condensation nuclei, and without them, clouds would not exist. The atmosphere would hold its moisture invisibly, releasing it only when temperatures drop far below what we normally experience. But the air is never truly clean. It is filled with microscopic particles from fires, volcanoes, ocean spray, and even the exhaust of human activity. And so clouds form, gathering around these invisible seeds, growing until they become visible. The next time you look up at a cloud, consider what it really is. Trillions of water droplets, each clinging to a particle too small to see, floating together in a formation shaped by wind and temperature. It is water, paused in its journey, waiting to fall. A raindrop begins its life high in a cloud, but it does not look like the teardrops we often imagine. At first, it is a tiny sphere, held together by surface tension. As it falls, it collides with other droplets, merging, growing heavier. The journey down can take several minutes, depending on the height of the cloud and the size of the drop. As the drop falls faster, air resistance begins to reshape it. The bottom flattens while the top remains rounded, giving it the appearance of a tiny hamburger bun rather than a tear. Larger drops oscillate as they fall, wobbling and jiggling, sometimes breaking apart into smaller drops that continue the descent separately. By the time a raindrop reaches the ground, it may have traveled several kilometers through the atmosphere. It has passed through layers of different temperatures, different pressures, different winds. It has merged with other drops and perhaps split apart again. And when it finally lands on a leaf or a rooftop or your upturned face, it is completing a journey that began with evaporation from some distant body of water, perhaps days or weeks ago. Rain is not just water falling, it is water returning, finding its way back to the surface after a long voyage through the sky. No two snowflakes are alike. You have probably heard this before, and while it is technically an oversimplification, the spirit of it is true. The number of ways that water molecules can arrange themselves into a snow crystal is so vast that the chance of two flakes being identical is vanishingly small. A snowflake begins as a tiny droplet of water that freezes around a particle of dust high in a cloud. From this seed, ice crystals begin to grow, extending outward in a hexagonal pattern dictated by the molecular structure of water itself. And the six-fold symmetry is built into the geometry of how water molecules bond with each other. As the crystal falls through the cloud, it passes through regions of slightly different temperature and humidity. Each change in conditions affects how the crystal grows, adding branches here, thickening arms there. The path through the atmosphere is unique to each flake, and so the final shape is a frozen record of its journey. Some snowflakes are simple hexagonal plates. Others are elaborate dendrites, with branches upon branches extending outward like frozen ferns. Some are columns, some are needles, some are irregular clumps of ice. The variety is endless, a gallery of frozen art produced by nothing more than water and cold. When morning comes and the world is covered in dew, you are seeing water that has traveled through the night air to settle on every surface. Dew forms when objects cool faster than the air around them, dropping below the dew point, the temperature at which the air can no longer hold all its moisture. On clear nights, the ground and the objects on it radiate their heat away into space. They become cooler than the surrounding air. When moist air touches these cold surfaces, the water vapor condenses, forming tiny droplets that cling to leaves, grass, cars, and spiderwebs. Fog is a similar phenomenon, but instead of forming on surfaces, the condensation happens in the air itself. When a layer of air near the ground cools below its dew point, the water vapor condenses into tiny droplets that hang suspended, too small to fall, too numerous to see through. And walking through fog is like walking through a cloud that has descended to meet the earth. There is something gentle about dew and fog, a softness to the world when water hangs in the air or beads on every surface. It is the same water that falls as rain and crashes as waves. But in these quiet forms, it seems almost tender. When sunlight passes through a raindrop, something magical happens. The light bends as it enters the drop, reflects off the back surface, and bends again as it exits. But different colors of light bend by slightly different amounts, and so the white light is separated into its component colors, spreading out into a spectrum. This is how a rainbow forms. Each color reaches your eye from a slightly different angle, with red at the top and violet at the bottom. And the arc of the rainbow is not a physical object in the sky, but a collection of light rays, each one coming from a different raindrop, all bending and reflecting at just the right angle to reach your eyes. If you move, the rainbow moves with you. It is always centered on the point directly opposite the sun, which is why you can never reach the end of a rainbow. It is a personal phenomenon, a private light show created just for you by millions of falling drops. Sometimes, if conditions are right, you can see a second rainbow above the first, fainter and with its colors reversed. This is caused by light reflecting twice inside the raindrops, losing some intensity with each bounce. Double rainbows are rarer, but they follow the same principles, the same geometry of light and water. And thunderstorms are among the most powerful weather events on Earth, and they are driven entirely by water. A thunderstorm begins when warm, moist air rises rapidly, carrying water vapor high into the atmosphere. As the air rises, it cools, and the vapor condenses, releasing heat in the process. This released heat makes the air more buoyant, causing it to rise even faster, pulling more moist air up from below. Inside a mature thunderstorm, updrafts can reach speeds of over 100 kilometers per hour. Water droplets are carried upward, freeze into ice, fall, melt, or carried up again, growing larger with each cycle. When they become too heavy for the updraft to support, they fall as rain or hail. The lightning that accompanies these storms is also created by water, or rather by ice. As ice particles collide within the cloud, they transfer electrical charge, with smaller particles carrying positive charge upward and larger particles carrying negative charge downward. This separation builds up enormous electrical potential, millions of volts, until it discharges in a flash of lightning. Thunder is the sound of that discharge, the rapid heating of the air along the lightning's path, causing it to expand faster than the speed of sound. What you hear rolling across the sky is the atmosphere itself, shocked by the sudden release of energy, water's stored heat finally unleashed. High in the atmosphere, above the clouds we normally see, there is a vast reservoir of water vapor. This vapor is invisible, carried by winds that circle the globe, moving from regions where water evaporates to regions where it falls as rain. Some of the most important of these atmospheric rivers flow from the tropics toward the poles, carrying moisture from warm oceans to distant continents. When these rivers of vapor encounter mountains or cold fronts, the moisture is forced to rise, cool and condense, producing storms that can last for days. The amount of water in the atmosphere at any given moment is relatively small, only about 12,000 cubic kilometers, a tiny fraction of Earth's total water. But this water turns over rapidly, cycling through the atmosphere every 9 days or so. The sky is a highway, constantly transporting water from where it is abundant to where it is needed. Tonight as you rest, water vapor is drifting overhead, invisible and silent, carried by winds you cannot feel. Some of it evaporated from an ocean thousands of kilometers away. Some of it will fall as rain tomorrow, or next week, or on the other side of the world. The journey never stops. The monsoons are among the most dramatic expressions of the water cycle on Earth. Each year, as the seasons change, vast patterns of wind shift direction, bringing months of rain to regions that would otherwise be desert. In South Asia, the summer monsoon carries moisture from the Indian Ocean across the subcontinent, producing rain so heavy that rivers overflow and fields flood. For centuries, civilizations have depended on this annual deluge, timing their planting and harvest to the rhythm of the monsoon. When the rains fail, famine follows. When they arrive, the land blooms. The monsoon is driven by temperature differences between land and sea. In summer, the land heats up faster than the ocean, causing air to rise and drawing moist ocean air inland. In winter, the pattern reverses and dry air flows outward from the cooling continent. Similar patterns occur in other parts of the world, in Africa, in Australia, in the Americas. The monsoon is a planetary heartbeat, a seasonal pulse of water that sustains billions of people and countless ecosystems. It is the water cycle made visible, written across continents in rain and flood and fertile soil. Now let us travel to where water becomes still, where it slows and freezes and waits. Let us drift into the world of ice. Ice is water transformed. When the temperature drops below 0 degrees Celsius, water molecules slow their frantic dance and lock into place, forming a crystalline lattice that is rigid and cold. The resulting solid is less dense than the liquid it came from, a rarity in nature, and this simple fact has shaped the history of life on Earth. We have spoken of how ice floats, insulating lakes and protecting the creatures below. But ice does more than float. It carves landscapes, it stores history, it reflects sunlight back into space, keeping the planet cool. It holds vast quantities of fresh water, locked away in glaciers and ice sheets, waiting to be released. Ice is patient. It moves slowly, when it moves at all. But over thousands of years, it can reshape mountains, gouge valleys, and push boulders across continents. Ice remembers. Trapped within it are bubbles of ancient air, pollen from vanished forests, dust from volcanic eruptions long forgotten. Tonight, somewhere on this planet, ice is forming. A pond is freezing over. A glacier is creeping forward. A snowflake is drifting toward the ground. Water is becoming stone, soft and cold and full of secrets. Glaciers are rivers of ice, flowing so slowly that their movement is invisible to the naked eye. They form in places where snow accumulates faster than it melts, piling up year after year, compressing under its own weight until the snow becomes ice. Over centuries, the weight of accumulated ice becomes so great that the glacier begins to flow. It moves under the pressure of its own mass, creeping downhill a few centimeters or meters each day, carving the landscape as it goes. Glaciers have carved some of the most dramatic features on Earth: the fjords of Norway, the U-shaped valleys of the Alps, the Great Lakes of North America. At the base of a glacier, the pressure is intense. On the ice, there is under so much weight that it can flow like a very thick liquid, bending around obstacles, squeezing through gaps. Rocks embedded in the bottom of the glacier scrape against the bedrock below, polishing some surfaces smooth and gouging, deep scratches into others. When a glacier reaches the sea, it calves, breaking off enormous chunks that become icebergs. These floating mountains of ice drift on ocean currents, slowly melting, returning their frozen water to the liquid sea. A single iceberg can take years to melt completely, a slow surrender to the warmth of the water around it. Antarctica holds about 70% of all the fresh water on Earth, locked in an ice sheet that covers nearly the entire continent. In some places, this ice is over 4 kilometers thick, built up over millions of years from countless snowfalls. If all the ice in Antarctica were to melt, global sea levels would rise by about 60 meters. Coastal cities around the world would be submerged. Entire countries would disappear. The geography of human civilization would be rewritten. But for now, the ice remains, a vast white desert that reflects sunlight back into space, helping to keep the planet cool. Antarctica is the coldest place on Earth, with temperatures that can drop below -80 degrees Celsius in winter. Almost nothing lives on the surface of the ice sheet, and yet the continent is not lifeless. Along the coasts, penguins and seals gather in enormous colonies, feeding on the rich waters that surround the frozen land. Beneath the ice, hidden from view, there are lakes. And these subglacial lakes are kept liquid by geothermal heat from below and the insulating weight of the ice above. They have been isolated from the outside world for millions of years, and scientists wonder what strange forms of life might have evolved in their dark waters. Snow crystals form high in the atmosphere, but when they land on the ground, their journey is not over. As snow accumulates, the crystals at the bottom are compressed by the weight of the snow above. They lose their delicate shapes, compacting into rounded grains, then into denser ice. This process is called fernification. Fresh snow is light and fluffy, with about 90% of its volume being air. But as it compresses over years and decades, the air is squeezed out, and the snow becomes firn, a transitional stage between snow and ice. Eventually, after centuries of compression, the firn becomes glacial ice, dense and blue and streaked with ancient bubbles of air. These air bubbles are time capsules. They contain samples of the atmosphere from the moment the snow fell, preserved for thousands or even hundreds of thousands of years. By drilling deep into ice sheets and extracting cores, scientists can analyze these bubbles and reconstruct the history of Earth's climate. The oldest ice cores recovered so far contain air from over 800,000 years ago. They tell a story of ice ages and warm periods, of carbon dioxide levels rising and falling, of volcanic eruptions and cosmic events. The ice remembers what the rest of the world has forgotten. Permafrost is ground that remains frozen for at least 2 consecutive years. Though most permafrost has been frozen for thousands or even millions of years, it underlies vast regions of the Arctic, from Siberia to Alaska to northern Canada, locking enormous quantities of organic matter in a frozen embrace. Within this frozen ground lie the remains of ancient plants and animals, preserved by the cold. Mammoth carcasses have been found in permafrost, so well preserved that their flesh is still intact. Seeds tens of thousands of years old have been recovered and germinated, producing living plants from the Pleistocene. But permafrost is also a repository of carbon. As ancient plants and animals died and were buried, their organic matter was frozen before it could fully decompose. Now, as temperatures rise and permafrost begins to thaw, this carbon is being released. Microbes that have been dormant for millennia are waking up, consuming the ancient organic matter and producing carbon dioxide and methane. This is one of the feedback loops that scientists worry about. As the climate warms, permafrost thaws, releasing greenhouse gases, which warm the climate further, which thaws more permafrost. The frozen ground is a sleeping giant, and it is slowly stirring. Icebergs are fragments of glaciers that have calved into the sea, and they are much larger than they appear. Only about 10% of an iceberg's volume is visible above the waterline. The rest lurks below, hidden beneath the waves, a frozen mountain extending deep into the cold water. The phrase "tip of the iceberg" has entered our language for good reason. What we see on the surface is only a fraction of what lies beneath. And this is true in more ways than one. Icebergs carry with them the history of the glaciers they came from, layer upon layer of ancient snow, now compressed into ice and set adrift. As icebergs drift on ocean currents, they gradually melt. Fresh water pours off them, mixing with the salty sea. Nutrients trapped in the ice are released, sometimes triggering blooms of plankton in the waters around them. The melting of an iceberg is not just a loss, but a transfer, a delivery of frozen resources to the liquid ocean. Some icebergs travel thousands of kilometers before they finally disappear. They drift from the Arctic into the North Atlantic, or from Antarctica into the Southern Ocean. They are transient monuments, temporary visitors from a frozen world, slowly surrendering to the warmth. When sunlight hits ice, something beautiful happens. Ice crystals scatter the light, bending and reflecting it in countless directions. This scattering is what gives snow its brilliant white color, as all wavelengths of light are reflected equally. But when ice is compressed, as in a glacier, the air bubbles are squeezed out and something changes. Dense glacial ice absorbs the longer wavelengths of light, the reds and yellows, while allowing the shorter wavelengths to pass through. This is why the ice in glaciers and icebergs often appears blue. The deeper you look, the bluer it becomes. This blue is not paint or pigment. It is the ice itself, interacting with light, revealing its inner structure through color. In the blue glow of a glacier, you are seeing the accumulated weight of centuries, compressed into something dense enough to change how light moves through it. There are places where you can walk into ice caves and be surrounded by this blue light, soft and ethereal, unlike any other color in nature. It is the color of time made visible, of water transformed by patience and pressure into something ancient and new. Now let us leave the cold behind and travel farther, beyond the atmosphere, beyond the familiar, into the darkness of space where water hides in unexpected places. For most of human history, we thought of water as something uniquely earthly, a gift specific to our pale blue planet. But as we have sent probes and telescopes into the cosmos, we have discovered that water is everywhere. It is one of the most common molecules in the universe, formed from hydrogen, the most abundant element, and oxygen, forged in the hearts of massive stars. Water exists in the frozen hearts of comets, in the atmospheres of distant planets, in the clouds between stars. It may flow beneath the surfaces of moons in our own solar system, harboring conditions that could support life. The universe, it turns out, is wet. and this changes how we think about our place in it. If water is common, then perhaps the conditions for life are common too. Perhaps somewhere, on a moon we have only glimpsed or a planet we have not yet discovered, water is doing what it does here, cradling chemistry, enabling complexity, waiting for life to emerge. Where did Earth's water come from? This question has puzzled scientists for generations, and the answer is still being written. But the leading theories point to the sky, to the bombardment that shaped our young planet billions of years ago. In the early solar system, Earth was hot and violent, bombarded by debris left over from the formation of the sun. Some of this debris came from the outer solar system, where it was cold enough for water to freeze. Comets, made largely of ice, may have delivered much of Earth's water, smashing into the young planet and leaving their moisture behind. Asteroids, too, may have contributed. Some asteroids contain hydrated minerals, water bound up in rock, which could have been released upon impact. The debate over whether comets or asteroids were the primary source is ongoing, with evidence supporting both. What is remarkable is that the water in your glass tonight may have arrived from beyond the orbit of Mars, carried by ancient impactors that no longer exist. The water in your cells, in your blood, in your tears may have traveled across the solar system before life on Earth even began. Well, you are drinking something older than the planet itself. Mars, our neighboring planet, is a frozen desert today. Its thin atmosphere cannot support liquid water on the surface. Any exposed water would either freeze or evaporate almost instantly. And yet, Mars was not always so dry. Billions of years ago, Mars had a thicker atmosphere and a warmer climate. Rivers carved channels across its surface, channels that are still visible today, dry and empty but unmistakably shaped by flowing water. There may have been lakes, perhaps even a shallow ocean, covering the northern lowlands. What happened to all that water? Some of it escaped into space, stripped away by the solar wind after Mars lost its magnetic field. Some of it sank into the ground and froze, forming vast deposits of subsurface ice that probes have detected in recent decades. The water did not disappear, it just changed form, retreating into hiding. Today, the search for water on Mars is also a search for life. If liquid water exists anywhere on Mars, even temporarily, in underground aquifers or seasonal brines, it might harbor microbes, remnants of a wetter past. Mars is a planet that remembers being wet, and we are only beginning to read its memories. Far from the sun, in the cold outer reaches of the solar system, there are moons that may hold more liquid water than all the oceans of Earth combined. These moons orbit the giant planets, Jupiter and Saturn, and they are among the most intriguing places in our search for life beyond Earth. Europa, a moon of Jupiter, is covered in a shell of ice perhaps 15 to 25 kilometers thick. But beneath that ice, scientists believe there is a global ocean of liquid water, kept warm by tidal heating as Jupiter's gravity flexes and kneads the moon's interior. The surface of Europa is young and active, crisscrossed by cracks and ridges where the ice has shifted. In some places, reddish streaks suggest that material from below has reached the surface, hinting at chemical exchanges between the ocean and the ice. What might live in that hidden ocean, in the darkness beneath kilometers of ice, is one of the most tantalizing questions in astrobiology. We have never seen this ocean directly. We have only inferred its existence from measurements of Europa's magnetic field, from the way the surface ice moves, from the slight variations in the moon's orbit. But the evidence is strong enough that missions are being planned to investigate further, to look for signs of life in water that has never seen the sun. Enceladus is a small moon of Saturn, barely 500 kilometers across, a tiny world of ice that should have frozen solid billions of years ago. And yet, Enceladus is one of the most active bodies in the solar system. Near its south pole, enormous geysers erupt through cracks in the ice, spraying plumes of water vapor and ice particles hundreds of kilometers into space. The Cassini spacecraft flew through these plumes multiple times, sampling their contents, and what it found was astonishing. The plumes contain water, of course, but also organic molecules, salts, and silica particles that suggest hydrothermal activity on the ocean floor. Deep beneath the ice of Enceladus, hot water may be venting from the rocky core, just as it does at hydrothermal vents on Earth's ocean floor. And on Earth, such vents are oases of life, supporting entire ecosystems without sunlight. Enceladus is spraying samples of its ocean into space, as if offering them for study. We do not yet have the technology to detect life in those samples, but future missions might. A tiny moon around a distant planet, erupting with water from an ocean we cannot see, may hold answers to questions we have asked since we first looked up at the stars. Titan, the largest moon of Saturn, is a world unlike any other in our solar system. It is the only moon with a thick atmosphere, a hazy orange shroud that hides its surface from view. And when the Cassini spacecraft peered through that haze with radar, it discovered something extraordinary. Titan has lakes and seas, but they are not filled with water. Titan is so cold, around minus 179 degrees Celsius, that water ice is as hard as rock. Any liquid water would freeze instantly. But at these temperatures, methane and ethane, which are gases on Earth, become liquid. Titan's lakes are filled with hydrocarbons, vast reservoirs of liquid methane pooling in basins near the poles. Rain falls on Titan, but it is methane rain. Rivers carve channels across the surface, but they flow with liquid natural gas. And waves may ripple across the lakes, driven by winds we cannot feel. It is a hydrological cycle, complete with evaporation, clouds, precipitation, and runoff, but built from entirely different molecules. Titan reminds us that water is not the only liquid that can shape a world. The processes we associate with water, the carving of landscapes, the cycling through atmosphere and surface, can happen with other substances under the right conditions. The universe is more creative than we imagine. Our own moon, so close and so familiar, was long thought to be completely dry. The samples brought back by Apollo astronauts showed no trace of water. The moon was a dead world, baked by the sun, with no atmosphere to hold moisture. But in recent decades, that picture has changed. Instruments aboard lunar orbiters have detected signatures of water ice in the permanently shadowed craters near the moon's poles. These craters are so deep that sunlight has not touched their floors for billions of years. Temperatures there drop to nearly minus 250 degrees Celsius, cold enough to trap any water vapor that drifts in. The amounts are small, mixed with the lunar soil rather than pooling as ice. But they are there, remnants perhaps of ancient comet impacts or of hydrogen from the solar wind combining with oxygen in the lunar rocks. The moon is not entirely dry after all. This water is of great interest for future explorers. If it can be extracted, it could provide drinking water, oxygen to breathe, and hydrogen for rocket fuel. The moon could become a way station for deeper journeys into the solar system, and water hiding in the shadows would make it possible. Beyond our solar system, in the vast spaces between stars, water exists in quantities that dwarf anything on Earth. Enormous clouds of gas and dust, called molecular clouds, drift through the galaxy, and within them, water molecules are abundant. These clouds are the birthplaces of stars. When a region of a molecular cloud collapses under its own gravity, it heats up, eventually igniting nuclear fusion. A star is born, and the material that does not fall into the star forms a disk, spinning around it, gradually clumping together to form planets. Water is present in these disks from the beginning. In the outer regions, where it is cold, water freezes into ice, coating dust grains and eventually becoming part of comets and icy moons. In the inner regions, where it is warmer, when water remains as vapor, eventually being incorporated into rocky planets like Earth. The water in your body was once part of such a cloud, drifting in the darkness between stars. It was gathered into the disk around our young sun, frozen into comets, delivered to Earth by impacts, cycled through oceans and atmosphere and living cells, until tonight it rests within you. Your water has traveled farther than you can imagine. There is a region in every solar system called the snow line, or frost line. It is the distance from the star beyond which water can exist as solid ice. Inside this line, the star's heat keeps water in vapor form. Beyond it, water freezes and can accumulate on planets and moons. In our solar system, the snow line lies between Mars and Jupiter, roughly in the middle of the asteroid belt. This is why the inner planets, Mercury, Venus, Earth, and Mars, are rocky and relatively dry, while the outer planets are giants with vast quantities of water ice in their moons and rings. The position of the snow line depends on the brightness of the star. Around dimmer stars, it is closer. Around brighter stars, it is farther out. And as a star ages and its brightness changes, the snow line can shift, potentially melting ice that was once frozen or freezing water that was once liquid. Earth sits inside the snow line, but not by much. Our planet's water exists as liquid largely because of our atmosphere and the greenhouse effect it provides. Without that protective blanket, our oceans would freeze. We live on a knife's edge, just warm enough for liquid water, just cool enough for it not to boil away. In the year 2011, when astronomers discovered the largest reservoir of water ever found, it surrounds a quasar, a supermassive black hole at the center of a distant galaxy, over 12 billion light-years from Earth. The water there exists as vapor, forming an enormous cloud that contains 140 trillion times the amount of water in all of Earth's oceans combined. This water is ancient. The light from that quasar has traveled for over 12 billion years to reach us, meaning we are seeing it as it was when the universe was only about 1.6 billion years old. Water existed in such quantities even in the early universe, formed from hydrogen and oxygen produced in the first generations of stars. The discovery confirmed that water is not a rarity in the cosmos. It is everywhere, has been everywhere, since nearly the beginning of time. The molecule that fills your glass, that falls as rain, that makes up most of your body, is one of the most common and ancient substances in existence. You are connected through water to the earliest epochs of the universe. The hydrogen in your water was formed in the Big Bang itself, 13.8 billion years ago. The oxygen was forged in stars that exploded before the sun was born. Water is older than the Earth, older than the sun, almost as old as time. Now let us return to Earth, to the water that flows beneath our feet, hidden from view but essential to life. Beneath the surface of every continent, there are vast reservoirs of groundwater, stored in layers of porous rock called aquifers. This water has filtered down through soil and stone, sometimes over centuries, filling the spaces between grains of sand and the cracks in limestone. Aquifers hold far more fresh water than all the rivers and lakes on Earth's surface combined. They are invisible oceans, silent and still, tapped by wells and springs, feeding the roots of plants, sustaining ecosystems in places where no surface water exists. Some aquifers are replenished quickly, refilled by rainfall that percolates down within years or decades. Others are ancient, containing water that fell as rain thousands or even millions of years ago. These fossil aquifers are being depleted faster than they can be recharged, pumped dry to irrigate crops and supply cities. When you drink from a well, you may be drinking water that last saw sunlight during the Ice Age. It has been waiting in the darkness, purified by its long journey through stone, and until someone drew it up into the light once more. Where limestone underlies the land, water becomes a sculptor. Over thousands of years, rainwater, made slightly acidic by dissolved carbon dioxide, seeps into cracks in the rock. It dissolves the limestone slowly, molecule by molecule, widening fissures into channels, channels into caves. The result is a hidden landscape, a world beneath the surface where rivers flow through darkness and chambers open into cathedrals of stone. This is karst topography, and it underlies about 15% of Earth's land surface. Within these caves, water continues its patient work. Droplets seeping through the ceiling leave behind tiny deposits of dissolved minerals. Over centuries, these deposits grow into stalactites, hanging from above, and stalagmites, rising from below. When they meet, they form columns that look like pillars in an underground temple. The shapes are endlessly varied, curtains and flowstones and delicate straws of crystal. Each formation is a record of water's passage, a sculpture carved one drop at a time. Some caves have been growing their formations for hundreds of thousands of years, undisturbed, unseen, until explorers brought light into the darkness. In the ocean, there are places where the water is so deep that it forms vertical shafts, plunging hundreds of meters into the seafloor. These are blue holes, underwater sinkholes that formed during ice ages when sea levels were lower and the limestone was exposed to rain. The most famous is the Great Blue Hole off the coast of Belize, a nearly perfect circle over 300 meters wide and 120 meters deep. From above, it appears as a dark blue eye staring up from the turquoise shallows, a portal to another world. Divers who descend into blue holes find themselves in a realm of silence and shadow. The water is often stratified, with a layer of hydrogen sulfide marking the boundary between oxygenated water above and anoxic water below. Below this layer, nothing breathes. The water is ancient and still. Blue holes are time capsules. The sediments at their bottoms contain records of hurricanes and climate changes stretching back thousands of years. Some hold the bones of animals that fell in during the ice ages, preserved in the oxygen-free depths. They are windows into the past, hidden in plain sight beneath the waves. Wetlands are places where water and land meet, where the ground is saturated for all or part of the year. They go by many names: marshes, swamps, bogs, fens. But they share a common character. They are neither fully land nor fully water, but something in between. Wetlands are among the most productive ecosystems on Earth. The shallow water and abundant sunlight support dense growth of plants, which in turn support insects, fish, birds, and mammals. Migratory birds depend on wetlands as rest stops on their long journeys, refueling in the rich feeding grounds before continuing on. But wetlands also serve quieter functions. They filter water, trapping sediments and absorbing pollutants. They store floodwaters, releasing them slowly and reducing damage downstream. They store carbon, locking it away in waterlogged soils where decomposition is slow. For centuries, wetlands were seen as wastelands, drained for agriculture or filled for development. More than half of the world's wetlands have been lost in the past century, but we are beginning to understand their value now, beginning to protect and restore these places where water lingers and life flourishes. Mangrove forests grow where no other trees can survive, in the brackish water where rivers meet the sea. Their roots are visible above the waterline, a tangled maze of arches and stilts that anchor the trees in soft, shifting mud. Mangroves are architects of their own habitat. Their roots trap sediment, building up the land beneath them. They protect coastlines from erosion, absorbing the energy of waves and storms. They provide nursery grounds for fish and shellfish, sheltering juveniles in the labyrinth of roots until they are large enough to venture into open water. The water among mangroves is murky, stained with tannins leached from fallen leaves. It smells of salt and decay, but this unlovely water is teeming with life, with crabs and snails and juvenile barracuda, with herons stalking through the shallows and crocodiles lurking in the channels. Mangroves exist at the boundary, neither fully marine nor fully terrestrial, adapted to conditions that would kill most other plants. They remind us that life finds ways to thrive in the in-between places, the edges and margins, the zones of transition. The Amazon River carries more water than any other river on Earth. At its mouth, the flow is so immense that it pushes back the Atlantic Ocean, creating a plume of fresh water that extends over 100 kilometers out to sea. The Amazon basin is the largest drainage system in the world, collecting water from an area nearly the size of the contiguous United States. Tributaries snake through the rainforests, fed by daily thunderstorms, draining highlands and lowlands alike. The river is so wide in places that you cannot see the other side. This vast quantity of moving water shapes the landscape and the life within it. Fish have evolved to eat the fruits that fall from flooded forest trees. Pink river dolphins navigate murky channels by echolocation. Flooded forests become underwater worlds for months at a time, and the creatures that live there have adapted to this rhythm of wet and dry. The Amazon is not just a river, it is a world, a liquid continent within a continent, a reminder of what water can create when given space and time and tropical rain. Now let us return to ourselves, to the water that flows within. Your body is approximately 60% water by weight, though this varies with age, sex, and body composition. Infants are about 75% water. Elderly adults may be closer to 50%. But whatever the exact number, water is the medium in which your life unfolds. Every chemical reaction in your cells takes place in water. Your blood, which is over 90% water, carries oxygen and nutrients to every tissue. Your lymph, another watery fluid, defends against infection. Your cerebrospinal fluid cushions your brain. Your tears wash your eyes. Your saliva begins the digestion of food. Without water, none of this would be possible. You could survive weeks without food, but only days without water. Dehydration disrupts every system in your body, from your kidneys to your brain. When the sensation of thirst is one of the most ancient and urgent signals your body can send. Tonight, as you rest, water is moving through you. It is being filtered by your kidneys, absorbed by your intestines, exhaled with every breath. You are a river in slow motion, a waterway that happens to be shaped like a person. Your kidneys are remarkable organs, filtering about 180 liters of blood every day. They remove waste products, regulate electrolytes, and adjust the concentration of your urine to maintain the body's water balance. Most of the water filtered by the kidneys is reabsorbed, returned to the bloodstream before it can be lost. Only about 1 to 2 liters end up as urine each day, a tiny fraction of what was filtered. The rest is recycled, used again and again. This efficiency is the result of millions of years of evolution in environments where water was not always abundant. Your ancestors survived droughts and deserts, and their kidneys learned to conserve every drop. You carry that legacy within you, a water-saving system refined by time. When you are dehydrated, your kidneys respond by producing less urine, holding onto water. When you drink too much, they release the excess. This constant adjustment happens without conscious thought, a silent negotiation between your body and its environment. Tears are not just water. They are complex fluids containing oils, mucus, antibodies, and enzymes. There are 3 types of tears, and each has a different composition and purpose. Basal tears coat the eyes constantly, keeping them moist and clear. Reflex tears are produced in response to irritation, washing away dust or onion fumes. Emotional tears, the ones that flow when you are sad or joyful, contain higher concentrations of stress hormones and natural painkillers. Crying, it seems, is not just an expression of emotion, but a way of regulating it. The act of shedding emotional tears may help the body return to equilibrium, releasing chemicals that have built up during stress. Tears are a kind of overflow valve, a way of letting something out that needed to escape. Only humans cry emotional tears. Other animals produce basal and reflex tears, but the tears of sorrow and joy appear to be uniquely ours. Water, leaving the body through the eyes, carrying with it the chemistry of feeling. Have you ever wondered why the sound of water is so soothing? The splash of rain, the murmur of a stream, the crash of waves. These sounds calm the mind in ways that are difficult to explain, but easy to feel. Part of the answer may be evolutionary. For our ancestors, the sound of water meant safety. It meant a source of drinking water nearby, which meant survival. It meant the absence of predators who tend to avoid noisy streams where they cannot hear approaching prey. The sound of water became associated with security, and that association lingers in our brains. Water sounds are also acoustically soothing. They are what researchers call pink noise, a type of sound where lower frequencies are louder than higher ones. This creates a gentle, consistent wash of sound that masks sudden noises and promotes relaxation. Tonight, if you cannot sleep, imagine the sound of water, a gentle rain on a roof, a brook flowing over stones, waves lapping at a shore. Let the sound fill your mind and let your thoughts drift on its current. If you gathered all the water on Earth and formed it into a single sphere, how large would it be? The answer is surprisingly small. The sphere would be about 1,385 kilometers in diameter, roughly the distance from London to Rome. Placed next to the Earth, this sphere would look tiny, a blue marble beside a basketball. All the oceans, all the rivers, all the ice and clouds and groundwater compressed into a ball smaller than the moon. Most of that water, about 97%, is salt water in the oceans. Of the remaining 3%, most is locked in glaciers and ice caps. Less than 1% of Earth's water is fresh liquid water available for drinking, for agriculture, and industry. This is the water that sustains 8 billion people and countless other species. This is the water that falls as rain, flows through rivers, fills our reservoirs. It seems abundant when you turn on a tap, but the numbers tell a different story. We live on a planet of water, but the water we can use is precious and limited. There is a curious phenomenon called the Mpemba effect, named after a Tanzanian student who noticed it in the 1960s. Under certain conditions, hot water can freeze faster than cold water. This seems to violate common sense. Hot water has farther to go to reach freezing temperature, so it should take longer. And yet, under the right circumstances, it does not. The effect has been demonstrated repeatedly, though the exact reasons are still debated. Some explanations involve evaporation. Hot water evaporates faster, reducing its volume and making it easier to cool. Others suggest that the distribution of temperatures within the water matters, or that dissolved gases behave differently at higher temperatures. The truth may involve multiple factors interacting in complex ways. The Mpemba effect reminds us that even something as familiar as water can surprise us. We have studied water for centuries, and yet it still holds mysteries. The simplest molecule can behave in ways we do not fully understand. The water you drink today has been on an unimaginable journey. It has existed for billions of years, cycling through the Earth system, passing through countless forms and places. Some of the water in your glass may have once been part of a dinosaur, recycled through the bodies of creatures that lived 100 million years ago. Some of it may have fallen as snow on ancient mountains that have since eroded to plains. Some of it may have drifted in the atmosphere of a young Earth before life had even begun. Water is never created or destroyed on Earth, only transformed. The same molecules that fill the oceans today are the molecules that filled them a billion years ago. The rain that falls tomorrow is made of water that has fallen before, perhaps many times in many places. You are drinking history. You are drinking time. Every sip connects you to the deep past and the distant future, to cycles that began before humans existed and will continue long after we are gone. And now, as this journey draws to a close, let the water settle within you. We have traveled far tonight, From the bent shape of a single molecule to the vast clouds of water vapor drifting between galaxies. We have sunk to the bottom of the deepest ocean trench and risen to the heights of thunderclouds. We have followed water through the veins of ancient glaciers and the arteries of your own body. Through it all, one truth has echoed gently. Water is not just a substance, it is a story written in hydrogen bonds and tidal currents, in raindrops and rivers, in the tears of a child and the geysers of a distant moon. You are part of this story. The water in your cells has circled the planet countless times. It has fallen as rain on forests that no longer exist. It has frozen in glaciers that have long since melted. It has been part of oceans, clouds, rivers, and living things beyond counting. Tonight, as you rest, water is still moving. Somewhere rain is falling on a quiet forest. Somewhere a glacier is calving into the sea. Somewhere, a child is splashing in a puddle, and an astronomer is searching for water on a world we have never visited. The cycle continues. It will continue long after you have fallen asleep. Long after this night has passed. Long after generations have come and gone. Water does not stop. It only transforms, only moves, only waits. So let your breath slow. Let your thoughts soften at the edges. Let the water within you find its stillness, even as the water of the world keeps flowing. You are made of water. You are made of stardust. You are made of time. And tonight, that is more than enough. Sleep well, and thank you for drifting with us through the quiet wonders of water. Good night.